Did you ever wonder why beta-carotene, that bright orange stuff in carrots, is actually good for your eyes? Or maybe how one type of molecule can show up in vanilla flavoring and in really important medicines?
It's pretty fascinating, right? And the answer, well, it digs deep into organic chemistry. We're talking about aldehydes and ketones today.
Exactly. Today we are doing a deep dive into these really fundamental compounds. We want to explore what makes them tick, their reactivity, and why they are such powerhouses in, well, everything around us. Our mission really is to demystify the key ideas about aldehydes and ketones. We'll look at how they're made, how they react, and why these reactions are so central from, like you said, vision, all the way to designing new drugs.
Yeah, hopefully you'll walk away understanding not just the what's, but the why. We'll unpack the concepts, the mechanisms, reactions, strategies.
And maybe even point out a few common places people trip up. So yeah, let's get into it. Okay, so at the very core of both aldehydes and ketones, you've got the carbonyl group. That's a carbon double bonded to an oxygen, CO. That's the star player here. Now, the difference between them, well, if that carbonyl carbon is attached to at least one hydrogen atom, that's an aldehyde. Think vanillin, the vanilla smell, or benzaldehyde, that's almonds. But if the carbonyl carbon is stuck between two other carbon atoms, then it's a ketone.
Like acetone.
Exactly. Acetone, nail polish remover, probably the most common one people know.
But they go way beyond that.
Oh, absolutely. Don't let those simple examples fool you. These things are crucial in biology hormones like progesterone, testosterone, and industry uses them too, like formaldehyde in certain vaccines. They really are foundational.
And what makes that CO bond so special, so versatile? It really boils down to one key property. It's electrophilicity.
Electrophilicity, meaning it loves electrons.
Precisely. Think of that carbonyl carbon as being a little bit electron poor, slightly positive. It's like a little magnet for anything electron-rich, which we call a nucleophile. See, oxygen is really electronegative. It pulls electron density away from the carbon atom in that double bond. That makes the carbon partially positive, or plus. So it's, let's say, ripe for attack by a nucleophile. And when that happens, the geometry changes. The carbon goes from flat, trigonal planar, sp2 hybridized,
Right.
to tetrahedral, sp3 hybridized, after the attack. And here's a really key point, something that explains a lot of their behavior. Aldehydes are generally more reactive than ketones when it comes to nucleophilic attack.
Oh, interesting. So aldehydes jump into reactions faster usually. Why is that? What makes them more eager, I guess?
It really comes down to two main things.
Yeah.
Space and electrons, or what chemists call steric effects and electronic effects.
Okay.
First, steric effects. Think about ketones. They've got two carbon groups, alkyl groups, attached to that carbonyl carbon. They're relatively bulky.
Can't be right.
Yeah, they take up space. Exactly. So when a nucleophile tries to come in and attack that carbon, it's kind of crowded. It's harder to get in there. Aldehydes, though, only have one alkyl group and then a tiny hydrogen atom.
Much less clutter.
Much less clutter. It's easier for the nucleophile to approach and react. That's the steric part.
Okay, that makes sense. And the electronic part.
Right, electronic effects. Those alkyl groups attach to the carbonyl carbon. They actually have a subtle electron donating effect. They sort of push a little electron density towards the carbonyl carbon.
Okay.
Now, a ketone has two of these donating groups. So they help stabilize that partial positive charge on the carbonyl carbon, making it a little less positive, a little less hungry for electrons.
Ah, so it's less attractive to the nucleophile.
Exactly. An aldehyde only has one alkyl group doing that. So its carbonyl carbon doesn't get as much stabilization. It remains more partially positive, more electrophilic.
And therefore more reactive.
Precisely. And understanding that reactivity difference is absolutely fundamental. It allows chemists to be really clever about designing reactions.
Got it. So reactivity is key. But before we dive deeper into the reactions themselves, how do we actually talk about these molecules, like the naming rules?
Yeah, you got to speak the language. Nomenclature is important. For aldehydes, the rule is the parent chain has to include the carbonyl carbon, and you use the suffix -al.
Like methanol, ethanol?
Exactly. And the neat thing is, the aldehyde carbon is always defined as carbon number 1. So you don't usually need a number locator for the L ending.
Convenient.
Very. Now, if the aldehyde group -CHO is attached directly to a ring system, we use a different suffix, carbaldehyde. So you might have cyclohexanic carbaldehyde, for instance.
Okay, carbaldehyde for rings. What about ketones?
For ketones, it's similar. You use the suffix 1, but because that carbonyl group can be in different places within the carbon chain,
You need a number.
you need a number, a locant, to say where it is, like pentan 2,1 versus pentan 3,1. Those are different molecules.
Right.
And while we prefer these systematic IUPAC names, you'll definitely still hear common names thrown around like acetone or benzophenone, especially for the simpler ones.
So the general process is still find the main chain with the carbonyl, number it to give the carbonyl the lowest number, identify substituents, put it all together.
Yep, the same fundamental naming strategy applies. Find the parent, identify and locate substituents, assemble the name alphabetically, and of course check for any stereochemistry, any chiral centers.
Great overview. Okay, naming covered. Now, how do we actually make these things in the lab? Where do they come from?
Good question. Synthesis is key in organic chemistry, and actually, a lot of the methods build on reactions you might have already encountered in earlier studies.
Okay, like what? For aldehydes?
For aldehydes, one common way is to oxidize a primary alcohol. But here's the catch.
Yeah.
You need to be gentle. You have to use a mild oxidizing agent.
Why mild?
Because primary alcohols can be oxidized first to an aldehyde, but then they can be oxidized again all the way to a carboxylic acid if you use a strong oxidizing agent. So to stop at the aldehyde stage, you need something controlled, like PCC, that's pyridinium chlorochromate, or DMP.
Okay, so PCC or DMP stops at halfway. Got it. Other ways.
Yeah. You can also get aldehydes from breaking double bonds in certain alkenes using ozonolysis, provided one of the alkene carbons has a hydrogen attached, or through a reaction called hydroboration oxidation of terminal alkynes.
Right, okay. And for ketones, is it similar?
Often similar, yeah, but sometimes a bit more straightforward. You can oxidize secondary alcohols to get ketones. And here you don't have to worry about over-oxidation, so you can use strong oxidizing agents like chromic acid, or the mild ones too.
Makes sense. Ketones are sort of at the end of that oxidation line.
Exactly. Ozonolysis works too if you start with the right kind of alkene. And adding water across a triple bond in a terminal alkene using acid catalysis, that usually gives you a ketone via Markovnikov addition.
Markovnikov addition.
And one more, especially for making ketones attached to aromatic rings, the Friedel-Crafts acylation, a really useful reaction.
So quite a toolbox for making them.
Definitely. Chemists can pick and choose the best route depending on the starting materials they have and the specific ketone or aldehyde they need to build.
All right, so we know what they are, why they're reactive, how to name them, how to make them. Now for the main event. What do they do? What are these key reactions?
This is where that electrophilicity really comes into play. The absolute core reaction type for aldehydes and ketones is nucleophilic addition.
Okay.
Remember that electron-poor carbonyl-carbon. A nucleophile, something with electrons to spare, sees that positive charge and attacks it. But how exactly this happens depends critically on the reaction conditions. Specifically, whether you're running the reaction under acidic or basic conditions.
Okay. So the pH matters a lot. What happens under basic conditions?
Under basic conditions, it's usually a straightforward two-step process. Step 1. The nucleophile directly attacks the carbonyl-carbon. Pow. Step 2. The oxygen atom, which now has a negative charge, picks up a proton, usually from the solvent or something else in the mix.
So attack first, then protonate.
Exactly. Think about a strong nucleophile like a Grignard reagent. It's also a strong base. It just attacks, bam, forms a new carbon bond. And these reactions with strong nucleophiles are often irreversible.
And you mentioned it's a strong base, so you can't have acid around.
Absolutely not. If you had strong acid around with a Grignard reagent, the Grignard would just react with an acid-base reaction instead of attacking your carbonyl. So basic conditions mean avoid strong acids.
Makes sense. Keep the strong players separated. What about under acidic conditions? Does the order flip?
It does. Under acidic conditions, the first step is actually protonation of the carbonyl oxygen by the acid.
Okay, so the oxygen gets protonated first. Why?
Because that makes the carbonyl carbon even more electrophilic. Putting a positive charge on the oxygen pulls even more electron density away from the carbon, making it super activated, really, really hungry for electrons.
Yeah.
And this activation step is crucial because under acidic conditions, you're often using weaker nucleophiles, like water or an alcohol. These guys aren't strong enough to attack a normal carbonyl effectively, but they can attack the protonated activated carbonyl.
So under acid, protonate first to activate, then the weaker nucleophile attacks.
Precisely. And this leads to a really important rule of thumb when you're drawing reaction mechanisms. If you're in acidic conditions, avoid drawing any species that looks like a strong base in your mechanism steps. And conversely, if you're in basic conditions, avoid drawing strong acids like H3O plus dead.
That sounds like a key tip to avoid common mistakes.
It absolutely is.
Yeah.
Following that simple rule Helps keep your mechanisms chemically reasonable. It's a very common pitfall for students learning this stuff.
Okay, great practical advice. So let's look at some specific nucleophiles, starting with oxygen ones. What happens when, say, water reacts?
Right, so water can act as a nucleophile. When an aldehyde or ketone reacts with water, it can form a hydrate. This is basically a molecule with two hydroxyl OH groups on the same carbon atom, what we call a geminal diol, or gem diol.
A hydrate. Is that stable?
Usually, the equilibrium actually favors the starting carbonyl compound. Water adds, but it can easily come back off. However, there are exceptions. For very simple aldehydes like formaldehyde, or for ketones that have really strong electron withdrawing groups nearby, the hydrate form can actually be quite stable and favored.
Interesting. Okay, what about alcohols instead of water?
Now that's a really synthetically useful reaction. When an aldehyde or ketone reacts with two molecules of an alcohol, typically under acidic conditions, you form an acetyl.
An acetyl. Okay, how does that happen? Is it like the hydrate?
It's a bit more involved, but conceptually you can think of it in two parts. First, one molecule of alcohol adds, similar to water adding, to form an intermediate called a hemiacetal. Hemi means half, right? So it's halfway to the acetyl. It has one OH group and one OR group from the alcohol on the same carbon.
Okay, hemiacetal first, then what?
Then, under those acidic conditions, the hemiacetal gets converted to the full acetyl, which has two OR groups attached to that central carbon. The second part involves several steps, protonating the SOH group of the hemiacetal.
To make it a good leaving group, like water.
Exactly, to make it leave as water. Water leaves, and this generates a very reactive intermediate. It's actually resonance stabilized. Then the second molecule of alcohol attacks this reactive intermediate. Finally, a deprotonation step gives you the neutral acetyl product.
So it's quite a few steps. You mentioned water leaves first, then the second alcohol attacks, not like an SN2.
Correct. That's another common mistake. Students sometimes try to draw the second alcohol attacking at the same time the water leaves, like a concerted SN2 reaction. But that central carbon is usually too sterically hindered for SN2. The water has to leave first to create that reactive intermediate, then the second alcohol adds.
Gotcha. Mechanism details matter. And these acetyls, they aren't just interesting structures, are they? They have a specific job in synthesis.
Oh, absolutely. Acetyls are incredibly useful as protecting groups.
Protecting groups? What do you mean?
Okay, imagine you have a molecule that has, say, both a ketone group and an ester group. And you want to react only the ester, maybe reduce it to an alcohol using a strong reducing agent like LiAlH₄.
Okay. But LiAlH₄ would reduce the ketone too. Right?
Exactly, reduce both. So what you can do is selectively protect the ketone first. You react the molecule with an alcohol and acid to turn just the ketone into an acetyl.
Ah. And the acetyl doesn't react with LiAlH₄.
Correct. Acetyls are stable under basic conditions, and LiAlH₄ reactions are typically done under basic workup conditions. So the acetyl just sits there, unreactive. You can go ahead and reduce your ester.
Clever.
Then once the ester reduction is done, you just add some aqueous acid. This removes the acetyl protecting group. It hydrolyzes it back to the original ketone. So you've selectively reacted the ester while keeping the ketone safe. It's like putting a temporary helmet on the ketone.
That's a really elegant strategy. Problem solving in action. And you mentioned this kind of chemistry shows up in medicine too.
Yes, a great example is fluocinolone. It's a topical steroid used in some eczema creams. It's actually delivered as a prodrug, meaning it's inactive initially, but becomes active in the body.
How does the acetyl help there?
Well, drugs with free hydroxyl groups sometimes have trouble penetrating the skin barrier effectively. Fluocinolone incorporates an acetyl structure. This form can pass through the skin more easily. Once inside, the slightly acidic environment of the tissue causes the acetyl to hydrolyze, slowly releasing the active anti-inflammatory drug right where it's needed.
Brilliant. Using chemistry for targeted delivery. Okay, let's switch gears from oxygen nucleophiles to nitrogen. What happens when amines react?
Nitrogen nucleophiles lead to some really important structures too. When aldehydes or ketones react with primary amines, that's amines with one alkyl group, RNH2 under mildly acidic conditions, around pH 4 to 5 is often optimal, they form imines.
Imines, what's the key feature there?
The key feature is a carbon-nitrogen double bond, CAN. These are also sometimes called Schiff bases. The mechanism has similarities to acetyl formation. You get addition first to form an intermediate called a carbonylamine, which has both an NMH and an NHR group. Then water is eliminated to form the CN double bond.
Okay, imamine formation, and this connects back to our eyes.
It does. This is the perfect time to circle back to that beta-carotene hook. Remember, carrots and vision.
Yeah.
Beta-carotene gets converted in our bodies to vitamin A and then to a specific aldehyde called 11-cis-retinol. In the photoreceptor cells of your retina, this aldehyde reacts with a primary amine group on a protein called opsin.
And forms an imine.
Exactly. It forms an imine linkage, creating a large molecule called rhodopsin. Rhodopsin is the pigment that actually detects light. When a photon of light hits rhodopsin, it causes a change in the shape of that retinal part, specifically around the double bonds, which triggers a whole signaling cascade that your brain interprets as vision.
Wow. So amine chemistry is literally how we see the world. That's incredible.
It really is a beautiful piece of biological chemistry.
Okay, so that's primary amines giving amines. What about secondary amines? Amines with two alkyl groups.
Good question. When aldehydes or ketones react with secondary amines, R2 and H, you don't get an amine. Instead, you form an enamine.
Oh, an amine. What's that structure like?
Enamine refers to a double bond, and amine refers to the nitrogen. So an enamine has a nitrogen atom attached to a carbon that is part of a carbon-carbon double bond, C.
Ah, okay. Nitrogen next to a CC double bond. How does that form?
The mechanism starts very similarly to enamine formation. The amine attacks the carbonyl, you get proton transfers leading to a carbonyl-amine-like intermediate. But the crucial difference is in the elimination step. To form an imine, you need to remove a proton from the nitrogen to form the C-name bond. But a secondary amine doesn't have a proton on the nitrogen once it's bonded to the carbonyl-carbon.
Right. It used its only NH proton in the process.
Exactly. So instead, a proton is removed from the carbon adjacent to where the carbonyl-carbon was. This forms the CC double bond, while the nitrogen forms a single bond to that double bond. That's your enamine.
Okay, subtle difference in the final step leads to a different product type.
Precisely. And this leads us to another useful reaction, the Wolff-Kishner reduction.
Okay, what does that do?
This is a powerful way to take a ketone or aldehyde carbonyl group and completely remove the oxygen, reducing it all the way down to a CH2 group, an alkane.
Carbonyl to alkane, how?
It's a two-step process. First, you react the aldehyde or ketone with hydrazine, H2N, NH2, to form an intermediate called a hydrazone, which is similar to an elamine. Then, you treat this hydrazone with a very strong base, like potassium hydroxide, and heat it up.
And what happens then?
The strong base and heat cause a reaction cascade that ultimately results in the CN bond being replaced by a CH bond, and importantly, it releases nitrogen gas, N2.
Ah, releasing a gas that usually drives a reaction forward, right?
Absolutely. The evolution of nitrogen gas makes the second step irreversible and provides a strong thermodynamic driving force to form the alkane product. It's a very effective way to deoxygenate a carbonyl.
So these reactions like acetyl and alanine formation, can they go backwards? Can you reverse them?
Yes, and that's actually very important. The reverse reaction is called hydrolysis. If you take an acetyl or an elamine or an enamine and treat it with water, usually with an acid catalyst, you can break those bonds and regenerate the original aldehyde or ketone.
So H plus in water undoes it.
Pretty much. This reversibility is key to things like protecting groups. You need to be able to take them off easily when you're done. And it's also used biologically.
Like the prodrug example.
Exactly. Think about methenamine. It's used as an antiseptic for urinary tract infections, UTIs. Structurally, it's kind of like a nitrogen analog of an acetyl.
Okay.
Now, formaldehyde is a really good antiseptic. It kills bacteria.
Yeah.
But you don't want to just swallow formaldehyde. It's toxic systemically. Methenamine is stable in the slightly base conditions of your digestive system. It gets absorbed and circulates. But when it reaches the urinary tract, the urine is typically acidic.
Ah, so the acidic conditions cause hydrolysis.
Precisely. In the acidic urine, methenamine undergoes acid-catalyzed hydrolysis and slowly releases formaldehyde right there in the bladder and urinary tract, where the infection is. It acts as a targeted delivery system for the antiseptic.
That is really clever chemical design, using pH triggers. Okay, we've covered oxygen and nitrogen. What about sulfur or even hydrogen?
Yep. Sulfur nucleophiles behave very similarly to oxygen ones. Thiols, RSH, react with aldehydes and ketones, again usually with acid catalysis, to form thioacetals, analogous to acetyls, but with sulfur atoms instead of oxygen.
Thioacetals. Okay, do they have any special uses?
They do. One neat trick with thioacetals is that you can react them with something called rainy nickel. This is a special preparation of nickel catalyst, and it basically chews off the sulfur atoms and replaces them with hydrogens.
So it removes the sulfur and puts hydrogens there. What does that achieve overall?
It takes the original carbonyl-carbon, which became the central carbon of the thioacetal, and reduces it all the way down to a CH2 group. So forming a thioacetal and then treating with rainy nickel is another way to reduce a carbonyl group to an alkane.
So it joins Wolff-Kishner and Clemmensen reduction as a method for CO to CH2.
Exactly. It gives chemists another option, depending on what other functional groups are present in the molecule.
And hydrogen nucleophiles.
Right. We should definitely mention those, though we often encounter them earlier. This is the reduction of aldehydes and ketones back to alcohols. Strong reducing agents like lithium aluminum hydride, LiAlH₄, or milder ones like sodium borohydride, NaOBH4, deliver a hydride ion, H, which acts as the nucleophile.
Attack by H.
Yep. Attacks the carbonyl carbon, pushes electrons onto the oxygen, and after a proton source is added, workup, you get an alcohol. Primary alcohols from aldehydes, secondary alcohols from ketones.
And if you make a new chiral center.
Good point. If the ketone isn't symmetric, adding a hydride will create a new chiral center at the carbon that used to be the carbonyl carbon. Since the hydride can attack from either face of the planar carbonyl group with equal probability, you typically get a 50-50 mixture of the two possible enantiomers, a racemic mixture.
Okay. Reduction to alcohols. Now, for what many consider the really powerful stuff in synthesis, making new carbon-carbon bonds, that's how you build bigger molecules, right?
Absolutely. CC bond formation is often the holy grail, and aldehydes and ketones are fantastic starting points for this.
What are the key tools here involving carbonyls?
Well, we already mentioned Grignard reagents. They are workhorses. RMGX adds an R group, a carbon nucleophile, to the carbonyl carbon, forming a new CC bond and leading to an alcohol after workup. Powerful, generally irreversible.
Okay, Grignards are one. What else?
Another important one is cyanohydrin formation. Here, the nucleophile is the cyanide ion, CMD. It attacks the carbonyl carbon.
Cyanide. That sounds hazardous.
Hydrogen cyanide, HCN, itself is indeed very toxic gas. But chemists usually generate the cyanide ion needed in situ, for example, by using sodium cyanide, NaCN, or potassium cyanide, KCN, with a bit of acid. It requires careful handling, of course.
Okay, so cyanide attacks, what do you get?
You get a cyanohydrin, which is a molecule that has both an alcohol group and a nitrile NDCN group attached to the same carbon, the one that used to be the carbonyl carbon.
And why is that useful? What can you do with the cyano group?
The cyano group is actually quite versatile synthetically. You can, for instance, reduce it down to a primary amine, CH2NH2, or you can hydrolyze it all the way to a carboxylic acid, COH. So cyanohydrin formation opens doors to other functional groups.
It's like a stepping stone.
Exactly. And interestingly, nature uses cyanide chemistry too.
Really? How?
Well, many plants produce compounds that release hydrogen cyanide when the plant tissue is damaged. It's a defense mechanism. For example, linamarin in cassava root, which is used to make tapioca, or amygdalin, found in the pits of apples, apricots, peaches.
So they release poison when something tries to eat them?
Basically, yes. These compounds are glycosides, and when they get hydrolyzed, for example, by enzymes released upon damage or even during digestion, they break down and release HCN. It's a pretty effective deterrent.
Wow. Okay, so Grignards, cyanohydrins, any other major CC bond makers?
Oh, yes. The big one, the really elegant one, is the Wittig reaction. This one, Georg Wittig, the Nobel Prize.
The Wittig reaction, what's special about it?
It's incredibly powerful because it allows you to take an aldehyde or a ketone and convert it directly into an alkene. It precisely replaces the CO double bond with a CH double bond.
Whoa. Swapping oxygen for carbon atoms in a double bond. How does that work? What's the magic ingredient?
The magic ingredient is a special type of reagent called a phosphorus silide, also known as a Wittig reagent.
A phosphorus silide? What on earth is that?
It sounds complicated, but it's basically a neutral molecule that has a carbon atom with a negative charge directly attached to a phosphorus atom with a positive charge, C bonded to P+5.
Okay, a charge-separated species, and this attacks the carbonyl.
Yes. The negatively charged carbon of the halide acts as the nucleophile attacking the carbonyl carbon. Then there's a cascade of steps involving formation of a four-membered ring intermediate containing both carbon, oxygen, and phosphorus, which then fragments to form the desired alkene, CC, and a phosphine oxide byproduct, PH3PO, which is very stable and drives the reaction forward.
That sounds amazing. Can you control which alkene you get, like cis or trans?
Ah, yes. That's one of those valuable aspects of the Wittig reaction, its potential for stereoselectivity. The structure of the alide itself often dictates the geometry of the alkene product.
How so?
Generally speaking, simple ides, often called non-stabilized alkylides, tend to predominantly form the Z-alkene, the cis isomer.
Okay, simple alkylides give Z. What about other types?
If the LiAlH has an electron withdrawing group attached to that negatively charged carbon, like an ester or ketone group, it's called a stabilized LiAlH because the negative charge is spread out by resonance. These stabilized LiAlHydes typically favor the formation of the E-alkene, the trans isomer.
So you can often choose your alide to target either the Z or the E alkene.
To a large extent, yes. It gives chemists significant control over the double bond geometry, which is crucial in making complex molecules, especially pharmaceuticals, where the exact shape is vital.
Yeah.
There's also a related reaction, the Horner-Wadsworth-Emmons, or HWE reaction, which uses phosphonate esters and also typically gives E-alkanes, often even more selectively.
So when planning a synthesis using Wittig, how do you think backwards?
Good question, retrosynthesis. You look at the target alkene, specifically the double bond. You can imagine breaking that double bond in two ways. One fragment comes from the aldehyde or ketone, and the other comes from the aldehyde. Usually you choose the disconnection that allows you to make the aldehyde from a readily available alkyl halide, ideally a primary one, because making the aldehyde itself often involves an SN2 reaction, which works best with primary halides.
Choose the easier path to the alphalide. Makes sense.
Exactly. It's all about efficiency.
Okay, that covers a huge range of reactions. When tackling a synthesis problem involving these, what are the key questions to ask?
You always come back to two fundamental questions. First, did the carbon skeleton change? Did you add or remove carbons? If yes, you need a CC bond-forming reaction like Grignard, cyanohydrin, or Wittig, or maybe ozonolysis to break bonds.
Okay, skeleton change. Second question.
Second, did the functional group change? Did you go from an alcohol to a ketone, ketone to alkene, carbonyl to alcohol? That tells you what kind of transformation you need: oxidation, reduction, nucleophilic addition, elimination, etc.
So analyze the skeleton and the functional groups.
Precisely. And the goal is always to find the most efficient route, usually the one with the fewest steps, using the reactions we've discussed.
Before we wrap up, how do we actually identify these compounds in the lab? What do they look like spectroscopically?
Good point. Spectroscopy is crucial. In infrared IR spectroscopy, the CO double bond gives a very strong, sharp absorption peak that's hard to miss, usually around 1715, 1720 centimeters 1 for simple ketones and aldehydes.
Around 1715, does anything shift that?
Yes. If the carbonyl is conjugated, meaning next to a double bond or aromatic ring, the peak shifts to a lower wave number, maybe closer to 1680 centimeters 1. Ring strain, like in small cyclic ketones, shifts it higher. And aldehydes have another clue. Weak peaks for the CH bond attached to the carbonyl, down around 2700, 2850 centimeters 1.
Okay, strong CO peak in IR plus aldehyde CH peaks. What about NMR?
In proton NMR, 1H NMR, the carbonyl group is electron withdrawing, so protons on adjacent carbons, alpha protons, are d-shielded, meaning they show up further downfield than they otherwise would, typically around 2.1, 2.4 ppm. The aldehyde proton itself, though, is unique. It's extremely d-shielded and shows up way downfield, usually around 9, 10 ppm. It's very characteristic.
10 ppm for the aldehyde proton, hard to miss. And carbon NMR.
Carbon NMR 13C NMR is also very telling. The carbonyl carbon itself is highly d-shielded because of the double bond to the electronegative oxygen. It gives the signal way, way downfield, typically around 2 ppm. It's often one of the furthest downfield signals in the spectrum and usually quite weak, but its position makes it easy to spot.
Around 200 ppm. Got it. So IR, proton NMR, carbon NMR all give clear signals for carbonyls.
Definitely. They work together to give you a clear picture.
Wow. What a deep dive indeed into aldehydes and ketones. We've really covered the waterfront, their basic structure, naming, how to make them, and this incredible range of nucleophilic addition reactions, from making alcohols and amines using protecting groups, all the way to building carbon skeletons with Grignards and the Wittig reaction.
They really are central players.
So what's the big takeaway for you, the listener? It's that this carbonyl group, CUS, is just a phenomenal workhorse in organic chemistry. It enables so many transformations that are absolutely crucial for making everything from, the flavor in your food to fragrances to complex, life-saving drugs, and even understanding how our own bodies work.
Yeah, it's a connection point between synthesis, biology, medicine.
Absolutely. And just think about the sheer elegance of it all. How changing something as simple as the pH can completely switch a reaction pathway. Or how nature itself has harnessed these exact same reactions for incredibly complex processes like vision or defending itself.
It really underscores how interconnected chemistry is. These aren't just abstract reactions on paper. They're happening all around us and inside us.
It's truly fascinating. Well, thank you so much for joining us on this exploration of aldehydes and ketones today. We hope you found it helpful. Keep that curiosity going, keep asking questions, and keep exploring the amazing world of chemistry.